final topic on carbonyl compounds is carboxylic acid derivatives and acylation. Carboxylic acid derivatives that you've come across already when we studied the topic of nomenclature earlier on in the term include esters, acid chlorides or acyl chlorides, and acid anhydrides. So we're going to look at the process of acylation, and the definition of acylation here is the process by which the acyl group is introduced, so the acyl group is introduced into another molecule, and this is the general formula of an acyl group. So you can see that carboxylic acid derivatives all contain the acyl group. If we look at the structure of acyl chlorides or acid chlorides, we can see that in both structures the carbon in the carbonyl compound is electron deficient because it's attached to an electronegative oxygen. In the case of acid chlorides, it's also attached to a chlorine atom, which is more electronegative than the carbon. So electrons are pulled away, resulting in a very electron deficient carbon atom. In acid anhydrides also, the carbon is attached to an electronegative oxygen and also another electronegative oxygen, rendering it also electron deficient. In the case of acid chlorides, Z is equal to a chlorine atom, and in the case of acid anhydrides, Z is equal to the O C double bond O R dash, and these are known as leaving groups. Now, obviously because the carbon is electron deficient, it's going to be attacked by nucleophiles, and the nucleophiles will attack the electron deficient carbon and the Z group leaves. Now, how fast the reaction is depends on three factors, and that is the size or the magnitude of the delta plus on the carbonyl group, on the carbonyl compound, and that depends also on the electron releasing or the attracting power of Z. That's the ability of Z to pull electron density towards itself, and also how easily Z is lost. That's how readily that bond breaks, the strength of the carbon-Z bond. So is the carbon-chlorine bond stronger than the carbon-oxygen bond here? And also how good the nucleophile is at attacking. If we look at the structure of acid anhydrides and acid chlorides, we can see that the carbon is attached to an oxygen which is much more electronegative in both cases, and also a chlorine. And therefore in both cases the carbon is rendered electron deficient. And from AS we know that electron deficient carbons are always attacked by nucleophiles. So let's revise nucleophiles. We know that nucleophiles must have a lone pair of electrons which they then use to attack an electron deficient carbon. So they donate their lone pair, forming a new dative covalent bond. The best nucleophiles for donating their lone pair are in order here. So primary amine is a much better nucleophile because it's to do with the availability of the lone pair on the atom that is behaving as a nucleophile. In this case, in a primary amine, the lone pair on the nitrogen atom, make sure you get the word atom in there, is more available for donating to the electron deficient carbon atom because of something called the inductive effect. So the inductive effect is enabled by the fact there's an alkyl group here, or a CH3 or a CH2, and that alkyl group is able to push forward a pair of electron density, making the electrons more available for donating. Whereas in ammonia, which is simply an amine but with a hydrogen instead of a CH3, CH2, hydrogens have got much less electron density and therefore the inductive effect is less. Alcohols are even weaker nucleophiles. Even though you've got an alkyl group pushing electron density forward, oxygen's lone pair of electrons are not as available as the nitrogens in ammonia. And even a weaker nucleophile than an alcohol is water because the hydrogens are low in electron density and therefore you've got a lower inductive effect. So this thing here is important to remember. The lone pair on the atom of the nucleophile is more available for donating to the electron deficient carbon atom. So let's revisit nucleophiles. We know the definition of a nucleophile is a species with a lone pair of electrons, which they use to donate that lone pair of electrons or attack an electron deficient carbon atom. The nucleophiles that we met last year, and the best nucleophiles are the ones with the greatest availability of this lone pair of electrons. So because acid chlorides and acid anhydrides will both react with nucleophiles, primary amines are much better nucleophiles than ammonia, which is better than alcohol, which is better than water. So it's to do with the availability of the lone pair. In a primary amines case, it's attached to an alkyl group here, and we know that the alkyl group has what's called an inductive effect. And the inductive effect is to push a pair of electrons, push electron density onto the nitrogen so the lone pair are more available. So when we go to ammonia, because hydrogens haven't got many electrons, the inductive effect is less, so the availability of the lone pair is also less. An alcohol, even though it's got an alkyl group here, the oxygen doesn't tend to donate its pair of electrons as readily as a nitrogen atom. And water, even less so than an alkyl group, because it doesn't have the inductive effect because it's just got two hydrogen atoms, which are therefore not able to push electron density onto the oxygen. So primary amines are the best nucleophiles because the lone pair on the nitrogen atom is more available for donating to the electron deficient carbon atom on either the acyl chloride or the acid anhydride. Make sure you get the word atom in there. It therefore follows that acid chlorides are much more reactive than acid anhydrides. In fact, they react really vigorously because the carbon-chlorine bond is much weaker. The speed of reaction also is determined by the reactivity of the nucleophile. And therefore, since the increasing reactivity of the nucleophile, it follows that an acid chloride reacting with a primary amine you'd suspect would be the fastest. However, there is something called steric hindrance, where with the amine, the R group tends to get in the way, and therefore it follows that ammonia actually is a better nucleophile. So rather than off by heart that amides are formed when acid chlorides react with ammonia and when acid anhydrides react with ammonia you get amides, it's much better to start off looking at the mechanism rather than try and memorize this table. So let's look at the mechanism. The first step of the attack is the lone pair of electrons on the nucleophile attacking the electron deficient carbon. So show the electron deficient carbon and then a bond being formed, a dative covalent bond going from the nitrogen atom to the carbon on the carbonyl group. Then the pi bond in the carbonyl group breaks and a pair of electrons moves on to the electron rich oxygen atom. The intermediate has a negative charge on the oxygen as both electrons from the double bond have moved onto the oxygen, and it therefore follows there must be a positive charge because on this side there is no charge, and therefore the intermediate must have no overall charge. This species is unstable, and therefore to retain stability the pair of electrons moves down to reform a pi bond, and then the group leaves, the leaving group here being the chlorine atom, and remember electrons must always flow in a direction, usually to the most electronegative atom, so they move onto the chlorine atom. Finally, the resulting amide loses its proton to the chloride ion, so hydrogen chloride is formed. Let's look at the equation for that reaction. The resulting product is an amide. In this case, the product is called ethanamide, and fumes of hydrogen chloride gas come off. Pause point. Write out the mechanism for the reaction between ethanoyl chloride and methylamine. So here is the outline for the mechanism for the reaction between ethanoyl chloride and methylamine. First of all, it's important to write the polarity and show the dipoles, the permanent dipoles on the ethanol chloride molecule, showing that the carbon is electron deficient. And it's also really important to show your lone pair of electrons on the nitrogen atom on your methylamine. The lone pair of electrons is donated to electron deficient carbon, and therefore electrons are pushed from the carbon and the pi bond between the carbon and the oxygen is forced to break and the electrons move on to the oxygen atom. There is an overall negative charge on the oxygen atom because the pair of electrons moved onto the oxygen, and therefore we must have an overall positive charge on the nitrogen atom to balance that out. This unstable intermediate is therefore stability is restored as the lone pair of electrons moves down and the pi bond reforms and the carbon-chlorine bond breaks and the chlorine atom leaves, taking a pair of electrons with it. So notice double-headed arrows, the movement of a pair of electrons. The resulting molecule this time is called an N-substituted amide because it's now got an alkyl group attached to the nitrogen atom. The name of this molecule is N-methyl ethanamide. And notice also a molecule of hydrogen chloride is released. Now, because propanoyl chloride has got 3 carbons, it becomes increasingly tiresome and time consuming to keep writing out the carbonyl group. So I'm going to tell the examiner I'm going to let that equal R for the rest of the molecule for an alkyl chain. In drawing methanol, I've drawn the OH group facing the propanoyl chloride, so we can easily draw the attack of the lone pair of electrons on the nucleophile. So the nucleophile this time is the propanol, attacking the electron deficient carbon. A pair of electrons moves, the pi bond breaks, and the pair of electrons moves onto the oxygen atom. So this time the intermediate has a positive charge, and as before, the lone pair of electrons comes back down to reform the pi bond between the oxygen atom and the carbon atom. The hydrogen atom here is lost and restores neutrality to the oxygen atom, and the resulting molecule is an ester. So we now have made an ester. So an acyl chloride or an acid chloride acylating an alcohol results in an ester and hydrogen chloride. The resulting ester molecule that's formed, as you learnt to name esters 2 weeks ago, has the alcohol methanol and the acid derivative propanoic group. So the name of the resulting ester is methyl propanoate or propanoate or propanoate. Methyl propanoate. So remember, acid anhydrides are simply 2 molecules of a carboxylic acid condensed together. So ethanoic anhydride is 2 molecules of ethanoic acid condensed together. So this is ethanoic anhydride. So this is going to react with ammonia. So first of all, let's put in the electron deficient carbons. And let's look at the attacking nucleophile, which is ammonia, NH3. Remember to show clearly your lone pair of electrons, and depending which carbon it's closest to depends where it will be attacked. So it could attack either carbon atom in this case. So the lone pair of electrons comes in and attacks the electron deficient carbon, and at the same time a pair of electrons moves onto the electron deficient oxygen atom with the breakage of a pi bond. Again, the intermediate has a negative charge on the more electronegative oxygen atom and a positive charge on what was the ammonia molecule. This unstable intermediate, a pair of electrons moves down, reforming the pi bond, and the leaving group this time is this part of the acid anhydride, and also a proton is lost. This time an N-substituted amide is formed, so this is ethanamide and a carboxylic acid, which is ethanoic acid. So reactions with acid anhydrides usually result in the formation of a vinegary smell. So in this reaction, the anhydride breaks and the ammonia, the attacking species, reacts to form an amide and ethanoic acid. The name of the mechanism that we've been describing, therefore, can be deduced by looking. Could you name the mechanism? Rather than try and remember the name of mechanisms, look at the species that's attacking, which we know is a nucleophile. Rather than remember the name of this mechanism, we look at the species, which is a nucleophile, and the first point is addition, because where there were 3 groups, here there are now 4. So it's a nucleophilic addition. However, in the second step, a small molecule is pushed out. So we call this mechanism. Why not test yourself? Describe mechanisms and write equations for the following reactions, by which time you really will be an absolute expert on acylation. So the first one you're going to do on paper is propanoic anhydride and ethylamine, followed by ethanoic, propanoic anhydride and water. Third one, butanoyl chloride and ethanol. And 4, salicylic acid and ethanoic anhydride, which makes aspirin. The formula for salicylic acid is given below, where it's a carboxylic acid group on a benzene ring and an OH group. So this is the nucleophile that attacks the ethanoic anhydride. In the first reaction, we've got propanoic anhydride and ethylamine, so well done if you've drawn those correctly. Now, I'm going to save time with those annoying alkyl groups by referring them to R, R dash. In fact, that could simply be R because they're both ethyl group. Oh no, they're not. So it's R and R dash, and then this ethyl group R double dash. And therefore, before I describe the mechanism, I substitute in the R groups, making the mechanism much simpler to draw. As before, the lone pair on the amine attacks the electron deficient carbon, the pi bond breaks and the electrons move on to the oxygen atom, getting a negative charge. Have you remembered your positive charge on the nitrogen atom? The leaving group this time is the OR group, and therefore the resulting species is an N-substituted amide and a carboxylic acid. Now let's reinstate the R groups to see the products. So the products of the reaction is an N-substituted amide. So this is N-ethyl propanamide, N-ethyl propanamide and propanoic acid. The final step is to write out a balanced equation for this nucleophilic addition elimination reaction. So now you've got the mechanism for the propanoic anhydride and ethylamine. Did you draw the structure of ethanoic propanoic anhydride correctly? Now there's the question of which carbon atom is going to be attacked by the nucleophile. Both of the carbon atoms are electron deficient because they're attached to an electronegative oxygen. And we then look at the surrounding groups. From the propanoic acid on the anhydride, we've got this 3-carbon chain, and from the ethanoic part, we've got this 2-carbon chain. Think about the attacking nucleophile. There's going to be less resistance coming on this carbon here because it's less crowded. We call it's got less steric hindrance. Also remember, alkyl groups are electron releasing, and therefore surely they could push their electrons onto this carbon here, making it slightly less electron deficient. So I'm going to go for the fact that possibly that this carbon is going to be attacked more readily than this carbon here. Before I draw out the mechanism, I'm going to call this alkyl group here R and this alkyl group R dash. It just makes it a lot easier and less cluttered when you come to write out the mechanism. Draw your nucleophile, which is the water molecule, the lone pair of electrons that are going to attack our electron deficient carbon. So as usual, the first attack comes from the nucleophile onto the electron deficient carbon, and therefore the pi bond breaks between the carbon and the oxygen, and the pair of electrons moves onto the oxygen atom. I'm going to put its dipole here. Again, the intermediate has a negative charge here, where the pair of electrons has moved onto the oxygen, and therefore to cancel out that negative charge, this oxygen here is going to have a positive charge. As before, the leaving group is this part of the molecule, so the pair of electrons moves onto the oxygen atom. As these lone pair of electrons moves back down to reform the double bond, and therefore to cancel out the positive charge, it loses a proton as the pair of electrons is returned to the oxygen atom. So we're left with a molecule of a carboxylic acid here, and another molecule of a carboxylic acid here. The proton that's released from this intermediate is here, so that that could be then attached to this carboxylic acid here. So all that remains is to now reinstate our R groups, and therefore the ethanoic propanoic anhydride, when hydrolyzed, broken up by water, breaks up back into its constituent carboxylic acids, ethanoic acid and propanoic acid. Pause point. Can you write a balanced equation for the hydrolysis of ethanoic propanoic anhydride? So this is a hydrolysis reaction. The water was the nucleophile, and the anhydride hydrolyzes back into its constituent carboxylic acids. The reverse process would be condensation. So have you written out the mechanism for the reaction between butanoyl chloride and ethanol? Again, for ease, I'm going to represent the alkyl groups with R for the rest of the molecule, R for this propyl group on butanoyl chloride, and R dash for the ethyl group on ethanol. Again, I've drawn the lone pair of electrons facing the acyl chloride. So now don't forget to put in your dipoles, and therefore that explains why the lone pair of electrons is going to attack our extremely electron deficient carbon, and the pair of electrons moves onto the oxygen atom. Remember, in the intermediate there is a negative charge on the oxygen, so there must be a positive charge to cancel out the overall charge on the alcohol. Now the lone pair of electrons moves down, reinstating the pi bond, and therefore the carbon can't have 5 bonds, so the leaving group, the chlorine atom, leaves, taking a pair of electrons with it. And remember, the proton leaves, returning its pair of electrons to the oxygen atom. So you can see in the resulting molecule is an ester and hydrogen chloride. And now it remains to reinstate your R groups. So the resulting molecule, your ester, the alcohol part is an ethyl group, and the carboxylic acid derivative part is a butyl group, so it's ethyl butanoate and hydrogen chloride gas. Pause point. Can you write out a balanced equation for the above reaction? So when an acyl chloride reacts with an alcohol, an ester and hydrogen chloride gas are formed. So now all that remains is to look at the mechanism for the acylation of salicylic acid and ethanoic anhydride to result in a drug commonly known as aspirin. Are you able to draw the structure of salicylic acid, whose common name is 2-hydroxybenzoic acid? This time, this is the nucleophile, the OH group on the 2-hydroxybenzoic acid. So for ease of drawing the mechanism, I've simply represented the rest of the molecule as R. To save drawing out the full structure of the bulky ethanoic anhydride, I've drawn half the molecule and represented that as R'. Because it's symmetrical, either of the carbon atoms can be attacked, so for simplicity's sake I've given this carbon here a electron deficient charge, and also therefore the oxygen is going to be slightly negative. So it follows that the lone pair on the OH of the 2-hydroxy benzoic acid is going to attack the electron deficient carbon atom here, and a pair of electrons is going to move onto the oxygen. So it's a lot easier to see the intermediate that's formed, and as with the last mechanisms, because it's nucleophilic addition, and now don't forget the positive charge on your oxygen because you've got on this oxygen because you've got a negative charge on this oxygen. As before, the carbonyl group is reformed as the lone pair of electrons moves back to form the pi bond, and the leaving group is here. So remember, electrons must always flow in the same direction. As before, the proton leaves. Here's the proton, and again we have an ester group, and here we have a carboxylic acid, so it's likely that because it's a weak acid it will pick up this proton here, and all that remains is to reinstate our R groups. So you can see here the OH group from our 2-hydroxybenzoic acid has now been acylated. So the acylation has come from the ethanoic anhydride. So we have now an ester. This molecule here is our carboxylic acid, which is ethanoic acid. So the ethanoic anhydride, part of it acylated our 2-hydroxy benzoic acid, and this molecule is commonly known as aspirin, and the side product is ethanoic acid. 2-hydroxy benzoic acid could also be acylated using ethanoyl chloride. Could you write out the mechanism for the reaction between salicylic acid and ethanoyl chloride to make aspirin, and also what is the side product? So for simplicity's sake, we have represented the rest of the 2-hydroxy benzoic acid molecule with an R, and this is behaving as the nucleophile. So the first step is a nucleophilic addition on the ethanoyl chloride. Lone pair of electrons moves onto the oxygen. So this is the unstable addition product, and remember now the pair of electrons moves back down to reform the pi bond, and the leaving group this time is the chlorine atom, because remember this is the weaker bond. So the chlorine atom moves off, taking a lone pair of electrons with it, and the hydrogen also restores neutrality to that positive oxygen. Now all we need to do is restore our R groups, and hey presto, we have our aspirin, but this time the side product is hydrogen chloride gas, which is quite inconvenient because hydrogen chloride gas is toxic, whereas the product of the last reaction was simply ethanoic acid, which could be sold on. Also, acyl chlorides, as you'll see in the next video, react violently and the reaction is less controllable. So the preferred reagent is ethanoic anhydride rather than ethanoyl chloride when making your aspirin. So really, to summarise, ethanoic anhydride is manufactured on a massive scale for acylation, and often in exams you'll be asked, why is it chosen? What's the justification on using it over ethanol chloride? So also, it's not only is it less corrosive, it's cheaper, doesn't hydrolyze with water, and therefore it's also safer because, as you just saw in the mechanism, the byproduct of its reaction is ethanoic acid, which can be sold on, rather than hydrogen chloride. Its major use is in the production of aspirin.
After just a moment or two of delay, we get a very vigorous reaction. You can see the liquid mixture boiling and bubbling. And again, if I bring in an open reagent bottle of concentrated ammonia, we see the white smoke created, which is evidence that HCl is indeed a byproduct of the reaction. So the two products, ethyl ethanoate, an ester with a fruity smell, and hydrogen chloride gas.
So in the video, some ethanol was added to some ethanoyl chloride, and you saw there was a violent reaction. And this is the case with all nucleophiles and acyl chlorides. They're extremely reactive. But how would you test to show that hydrogen chloride was a byproduct? You saw in the video that he used ammonia, concentrated ammonia, where there were fumes of ammonia produced. Can you write an equation for the reaction of the hydrogen chloride with the ammonia? Correct. The white fumes are ammonium chloride, because remember, in this reaction, the ammonia donates its lone pair of the nitrogen atom donates its lone pair of electrons to a hydrogen, and the ionic product, ammonium chloride, is formed, which is seen as the white fumes. How else could you test for the hydrogen chloride gas? Correct. You could use universal indicator paper. It's damp, so the hydrogen chloride will dissolve in it, forming hydrochloric acid, and the universal indicator paper, as you know, will go red. Some of the hydrogen chloride would dissolve into the ester. How could you tell there were chloride ions present? Well done, you can remember from your group 7. To test for chloride ions, you simply add some dilute nitric acid to get rid of unwanted carbonates, and then add silver nitrate solution, and a white precipitate would form.
You will see that a white precipitate forms immediately.